Hello, I'm going to talk in this lecture about quantitative analysis methods. We begin, as you can see, with a picture of Oshodi market in Lagos. Now, in this market, which gets very crowded on busy days, I'd like to imagine that we can select some of these people here to interview. And here we've selected 5 people, and we've gathered data from these 5 people, and among the data we've gathered is data on sex and age. So over here we spoke to somebody who was male, 17 years old. Down here we spoke to an individual who was female and 14 years old. And there's the data we got from those 5. Now, if we put all the data together, here we've got the data together into a table. We can see that here I've just numbered the individuals for reference. Here's the sex and here's the age. Now, what can we tell from this so far? Well, among that group of 5 people, we found that there are 2 females. Now, 2 out of 5 is 40%. So 40% of those 5 people are female, which means that 60% of the males. You look at their ages, and here, instead of working out the average age overall, I've split it into females and males. So for the females, if you add up the average age, or the age of 19 and 27, that gives you 46, divide by 2, you get 23. Do the same calculation for males, add the male ages up, divide by 3, you get 26. So the mean ages are 23 years for females, 26 years for males. So the males are slightly older. So that's what we've found out so far about that group of 5 people. The chances are, however, that if we're interested in what goes on in this society or this market for any reason, although it's nice to know about these 5 people, it could well be what you really want to know is something about the whole crowd of people, or the whole set of people that take part in market activity. The whole crowd is what we're really interested in. So, based on this information about 5 people, another question we can ask is this: what can we tell about the rest of the people? Now that gives us this difference between what we call descriptive statistics and inferential statistics. The picture you have to have in your mind is the distinction between the sample and the population. In both cases here, the population is all the people in that market, whereas the sample is just the 5 people we've talked to. And in general terms, when you get data on a sample, descriptive statistics looks for patterns in the data. So here, I've drawn a picture of a pattern. I've observed a pattern in here. And descriptive statistics just describes to whoever your audience is, what patterns have you found in the data that you've got. So for example, in the data we have, among those 5 people, we found 40% of them are female, and we found the mean age of men was higher. It's 26 compared to 23. So that's our 2 patterns that we've spotted so far. When we turn to inferential statistics, what we're interested in there is, having already got a pattern of some sort in the sample, inferential statistics helps us work out the likelihood, or the chance, or the probability. What's the likelihood that the patterns we've already found in the data we've got also exist in the population? So, in other words, in the whole market, what's the chance that all the people, about 40% of them are female? And what's the chance that in the whole crowd in the market, the mean age of men will turn out to be higher? So with these patterns here that we found in the 5, what's the chance that they hold for the whole market? That's the problem of inferential statistics. Notice, of course, that to do inferential statistics, you've also got to do some descriptive statistics, because you have to find these patterns in the first place, and then you go a stage further by asking about the whole population. Let's look at some techniques used in descriptive statistics. And to illustrate these, I've got this simple data set which I've got in Excel. So we'll try and switch to that. Will let us do. And here's the data in Excel. We can see we've got data from a number of people, about 30 people, and their sex, the language they speak, their views on a number of issues using this scale of 1 to 5. And these 4 issues here. The age and the income in TQ, I can't remember the currency, TQ per day. Now, we can use some descriptive statistics to describe the patterns in this data. So let's see, let's look first at their views on multi-party elections. We'll look at these quantitative data here. So multi-party elections, it'd be nice to get a summary at the bottom here. What are their views? So how can we describe their views overall? And one way you can do it is to look at the average view. And one way of doing that is to look at what's called the mean. So we're going to get here the mean. It's going to be the mean of, make it bigger, you can see what I'm doing. The mean of all their views on multi-party elections. And what I type in here is, well, first I note that the numbers are in the cells from C3 down to C32. So I'm typing equals. Equals tells Excel that he's got to look for a formula. And I can type in C3 to C32, exactly like that. Press enter and it should work it out for me there. 3.16667. So the average age using the mean is 3.1667. So it's somewhere slightly more than half way between 1 and 5. Now there's another kind of average I could have used, which is this one, the median. And to get that in Excel, you just type in equals median. And you have to put the same thing in there, C3 up to C32. That tells it where the numbers are. Press enter. The median's 3. Now to see what that is, to see what the definition of median is, we need to just look at these numbers a bit more carefully. Move this out of the way for a second. We take this set of data here and we sort it. Just this bit here. I'm going to sort it by column C, smallest to largest. So that sorts everything from smallest to largest. Well, very good. What's that got to do? Well, there are 30 numbers here. Because there's 32 rows, but the first 2 are just taken up with labels. So we've got 32 numbers. And now I've put these into order of their views on elections. If I go halfway, that would be about the 15th person, wouldn't it? 15th or 16th person. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the 15th person, their view was 3, and the 16th person, their view was 3. So in the middle here, the views are 3. And that's what the median is. It says, if you were to put all the numbers in order, what would the view of the person in the middle be? Now the other one we can use, you may have heard of, is the mode. That's another version of average. To get that one, type in mode. And you can then type in C3 up to C. There's a quick way of doing it, which is just to use the cursor to shade in numbers and see it. It's automatically put C3, C32 there. Oh, the mode is also 3. Now the mode is the one that comes up the most. You can see there are most 3s. Now something really handy about Excel is that once you've done that for one column here, you can just copy that, which I've done like that. By pressing Control C, I copy that and then paste it. And just automatically it will do the rest of them. And what you can see is, if I blow it up a bit, you can see here that the formula was average in cells C3 to C32. Here it's changed it to average D3, C32. So when you copy this way, it automatically changes the letters, so they go up to follow these letters along here. So it's very quick to work out statistics once you've got a couple of formulas typed in. So we can compare the mean views. It looks like, according to the mean, the average view was strongest on this health clinic fees thing. They felt most strongly, and the weakest was the views on privatisation. They weren't that bothered about. The median, they seem to have The median is one where you put them in order. The middle person thought 3 for those and thought 4 for that one. And the one that came up most often was 3 in all these cases, except for there it was 4. I think you can see that. Let's put the whole thing in order of health clinic fees and see if that makes sense. So we'll source it again, but this time on column F. You can see it in, nobody said only 1 for health clinic fees, but most people said 4. You can see it right in the middle was 4 this time. You count down 15 or 16 people, that's around here, that's 4. Now, if there's 3 different sorts of average, one problem that you immediately get is, well, which one should you use? So you might like to think about which of these are more or less useful in each of these cases. Particularly when we get to income over here. The mean income, which is when we add them all up and divide by how many numbers there are, that's 279 TQs per day. The median was slightly less, 260. And the mode was 252. Let's sort them in order of income, which is in column H. So that's sorting from the smallest income to the highest income. So 260, about 15 or 16 people down, plus the 2 you started with, about 17 or 18. So it should be around here somewhere. I believe that's the median. The median is 260.5. That's worth looking at because there isn't a 260.5 in this column. The reason is that this is the 15th person, this is the 16th person, but there isn't a person right in the middle because there's an even number of people. There are 30 people, so it's halfway between the 15th person down and the 16th. If you go halfway between these two numbers, you get this. The mode, however, is the one that's not very useful here, because when numbers are like this, there are so many different possible numbers you could have that most of them are just going to occur once. And it just so happens there's a couple of 252s, there are 3 252s. I think everything else is, there's a couple of 334s, a couple of 271s. But the mode is not very useful when you have a large number of different possible values. It's not necessarily going to represent the values too well. More representative are the mean and the median. Now finally, before we leave this data set, I've dismissed these as being qualitative, but that does not mean you can't do any quantitative analysis. Because there's only a certain number of categories here, and there's 2 possible categories here, you can still do some counting, so it's still quantitative in a sense. A command that you can use for this in Excel to make it count things automatically is this. You put in the same thing here, the range of cells. So that would be A3 up to A32. M. F. 9. Do the same thing for counting the males. So to count, that formula looks in those cells and sees how many Fs there are. That looks and sees how many Ms there are. So you've got 9 females and 21 males. And then if you wanted to, you could then do this. You could 9 divided by this plus this is 0.3, which means that 9 out of the 30 is 0.3, which is 30%. If you want to see it as that, you could times by 100. Give you the 30%. So 30% are female out of this group, and the other 70% are male. So you can do some quantitative analysis even when you've got data which looks qualitative. here there are some categories, so that is really if you see these as separate categories, then you can view it as quantitative data. Similarly, you could count up here how many Arjet speakers, how many Earden speakers, and how many Lengit speakers, and look at the proportions there. So you can count them. You might like to think about which of these, mean, median, and mode, you could use with this simple categorical data. If you pause the recording and think about which of these you could use with these two columns here. And of course, the answer is that you could use mode, because the mode would be the one that comes up most frequently. So here, in this column here, it's the males. This one that I've counted here is the most frequent. That's the mode, is male. In this one, I'm not sure what it is. It's not. You have to count out how many Arjets, how many Eardens, how many Lengits. One of those three values would be the mode, but it wouldn't make any sense to work out the median or the mean of those two. You just couldn't calculate it. So there's three basic statistics you can use: the mean, the median, and the mode. And the mode you can also apply to this kind of categorical data, treating that as quantitative. So, using some simple Excel commands and this data about people's views on a number of issues and their age and income, we've illustrated these techniques in descriptive statistics: the mean, the median, and the mode. And these all describe how big the numbers are on average. These can all be referred to in different contexts as the average, which is why we tend in statistics to avoid the term average, because it could mean either any of these three things. But they all do describe how big the numbers are on average, and what we call that is the level of data. Taken as a whole, are these numbers bigger or smaller? And those are three descriptions. Now if we go on to another set, and in this set's a slightly bigger database, and it's about household land holdings in 4 rural areas. So here's the household number. Here's area A, B, and C, and D. Let's just see if we can locate that in the actual Excel file. If it'll let us do it. Yeah, there it is. Now if we look at these households, I'd like you to have a look at the data as I scroll through. And would you say that the level in A or B or C or D is the highest? Clearly there's a lot of variety. You can see there's one with a very small one here, bigger one. In B there's one with hardly any land here, a bigger one there. So there's a lot of variety. But on average, have a look at these numbers and see if you can put them in order. What's the biggest and what's the smallest? Yeah. Which on average is going to be bigger? Really hard to do just looking at numbers, which is why we can start with this database just recapping to see what the statistics suggest. And here I've put in those formulas, so there's the average, the median, the mode, and so on. I've also put in the maximum and the minimum, which is the obvious one. Max gives you the maximum, min gives you the minimum. I've done it for all of them. Now, according to these then, C here is the one that on average is the biggest. I think that you can tell that because there's quite a few people that have got large land holdings, even though there's others with very little. So looking at the averages, mean and median agree that the area B has on average the largest land holdings, D the next largest, then C, and then bringing up the rear A with the smallest. They both, mean and median, both give a consistent picture. Mode, however, is sort of a bit all over the place. It thinks that C is the biggest, or D is the biggest, and then C, and then A, and then B. And you might like to try and remember why mode really is not a very good statistic to use in this context. And if I'll pause for a second while you think about that. Why is mode not so good here? And of course the answer is because there are so many different possible values that it's likely that most of them will only occur a few times. And the one that just happens to occur the most isn't really a very good guide as to what the average level is. So mode with such a large number of possible values is pretty hopeless. So we probably wouldn't even bother reporting that. Maximum and minimum, well, they suggest that, again, this is the biggest, but even though this is the second biggest on average, the second biggest average is that one. Oh, it still follows the order just about, except this one's slightly bigger than that one. And the minimum, they're all pretty much the similar minimums, except the minimum tells us that D is the only area where there are some landless houses. At least one household has got no land at all. Presumably they're people that are not working agriculture or they're landless labourers. Right, so that's levels. Now, there's another thing that's different about these villages. Not only are the levels different, but also, even though we notice that in each village there's differences between who's got more and less, in some villages the differences are more pronounced than others. And very often in development we're interested in that, the differences between, the degree of difference between people that have a large amount of something and people that have a small amount of something. And whether there's anything to do with distribution of resources or inequality. So as well as looking at the level, we'd like to have a measure of the inequality, or as we put it in statistics, the spread. Which village or which area has got land holdings which are more spread out. Now there's different statistics we can use to measure this, but have a look as I scroll up and down. Which one would you say has got the biggest variety and which has got the smallest variety? Then I'll put some figures in and we'll try and get some numbers for that. Now, all of the ones I've got in here so far are the measures of level. Now we're going to have some measures of spread, or sometimes called dispersion. And the simplest one of all is the range. And the range is just what's the difference between the person who's got the least, the household with the least, and the household with the most. And to calculate that, you just have to to take the maximum and subtract the minimum. So here, you can put a formula in Excel equals cell C210, which is that one, subtract cell C211. So there's a range of 2 hectares here, from the minimum to the maximum. That's the formula I put in. Now, as before, I can just copy this, and in Excel, you notice that when the cursor goes across that bottom of the cell like that, it turns into a small black cross. That means I can then click it and drag, and it will just copy across there. Give me the formula in the others. So there are the ranges. The biggest range is this one, so that's where the biggest spread according to the range. And the smallest, the one that's most tightly bunched, is that one. There's the smallest difference between people with least and people with most. This is somewhere in between. So perhaps that would confirm the impressions you got from scrolling up and down. Probably these two, A and C, are hardest to tell apart just with a naked eye. Now that's not the only measure of spread, because the problem with this one is that it's entirely dependent on 2 values, the maximum and the minimum, such that if I was to fly in as a very rich person and buy up a whole bunch of land here, okay, there'd be less land available. But say I just bought up a lot of land here, perhaps by buying into a neighbouring territory, and I bought 50, then all of a sudden the one with the largest range would be number A, or area A, just because of that one person changing, the maximum changing. Whereas really, for the vast majority of the households, the experience is the same. So the problem with this measure of spread is it's entirely dependent upon the minimum and the maximum. So it's vulnerable to a change in either of those. Let's go back to what it was before. So what you'd like is something that would take account of more of the numbers. In reaction to the fact that the problem there was being dependent upon the extremes, you want to have something more representative. An obvious move is to look just at the values in the middle. And what I'm going to put in here is something called the lower quartile and the upper quartile. Now these, again, are strictly speaking measures of level. And I'll type it in before I tell you what it means. Oops, okay. Be demonstrating how to do this. Put another lesson. You have to put another number in here, which is 1. So that's the formula. It's quartile, then as before, this is the range of cells, and you have to give another number afterwards. I'm putting 1. And it's 1 because it's lower quartile. I've just copied the same range of cells there. I put in the next one is 3. The same range of cells, and I put 3. Now let's try and explain what that means. The way I'll try and explain it is that I'm going to sort these again. So there we've sorted it on column C. And now, if you remember, there are 200 households. So if I go down to the 100th household, I'll find the value of the 100 is 1.2. That's, well, and the 101 is at 1.2. So because there's 200 households, the middle one would be somewhere in here somewhere. There's an even number. So the median would be 1.2. Which is why the median is 1.2. But what about these ones here? What's this 0.2 and 2? No, sorry, the 0.9 and the 1.5. Well, the quartile means instead of going halfway through to the 100th observation here, I go a quarter of the way through. So there's 200 numbers, so I go to the 50th. So, and there's the 0.9. If I go to the 150th, that's 3 quarters of the way through. 150, 3 quarters of the way through, that's the 1.5. So these, the lower quartile and the upper quartile, they extend the idea of the median. Instead of looking halfway, you put them into order and you look a quarter of the way through and 3 quarters of the way through. I'll leave these sorted in that order. Copy these across. You can see. So a quarter of the way through, B is 1.8 and so on and so on. And the upper quartile, again here, the upper quartile, that's the 3 quarters of the way through it. 6.3, so already quite high, and 3 quarters of the way from the smallest to the largest in D is 2.9. Now these are all just measures of level still. To get the measure of the rate of the spread, what I do is I look at the difference between the lower quartile and the upper quartile, because the middle 50%, out of those 200 households, the middle 100 between here and here. So if I do something similar to the range, but instead of working out the distance between maximum and minimum, I work out the distance between the lower quartile and the upper quartile. That tells me what space contains the middle 100, the middle 50% of households. And that's got this lovely name, the interquartile range. So we need to get the upper quartile and subtract the lower quartile. You can do that for others as well. So in village A, the middle 100 households, those middle half, are contained in a range of 0.6 hectares from the smallest to the largest holding. B is 4.5, C 0.3, and D 1.1. So again, that agrees with the order of spread given by the range. This is the smallest, that's the next one up, that's the next one up, and that's the biggest. Again, smallest, next one up, and the biggest. But these refers to the middle 100 households, so it's leaving out any changes in the extremes. So if I come in here and I buy up lots of land, it doesn't make any difference to the interquartile range. So it doesn't make any difference to the spread of the middle half. So the advantage of the interquartile range then is it's less sensitive to the extreme values at either end. So the range and the interquartile range can be used to describe the spread of our data. The disadvantage of these is that they take account only of 2 numbers. The range takes account of the minimum and maximum. The interquartile range is not affected by those extremes, but it's still based on only 2 numbers, the lower and upper quartiles. It's much better to have a range of spread that takes account of every single number in the data set. So if you change one of these numbers, you'll slightly change the measure of spread. And the statistic that we use when we're trying to talk about spread most frequently is a statistic called the standard deviation. We calculate the standard deviation to give us a measure of spread whenever we're really interested in how numbers are spread out. For example, when we're talking about inequality or the distribution of resources, it's critical to know about the spread of data. We use a standard deviation. Now, even though for practical purposes you always use a computer or a calculator to give you this, it's important to understand the concept of what it means. So I'm going to show you how to work it out just with a few numbers. So here we've got a few numbers to find the standard deviation of these numbers, 1, 3, 6, 7 and 8. Now to start with, we need to work out roughly where the middle of these numbers is, and to do that we need to calculate the mean. So to find the mean, we're going to have to add the numbers up, so that's 4, 10, 17 plus 8 is 25. And to calculate the mean, of course, we have to divide the 25, which is the total, by 1, 2, 3, 4, 5 numbers. To find that the mean is more or less 5. So the mean's somewhere in here somewhere. And you might notice in statistics books and in publications this symbol, this is a Greek letter mu. It's often used to stand for the mean. So we're showing that the mean is 5, about here. Once you've established that, then this calculation of spread called the standard deviation looks at how far is every single number from that central mean. We start with the 6, well, that's not very far away from this mean. It's just 1 away. Very close. The 7, well, from 5 up to 7 is 2. This number is 2 away from the mean. This number 8, well, from 5 up to 8 is 3. And we have to do these here, well, from 6 down to, from 5, from the mean of 5 down to 3, that's 2. And from the mean of 5 down to 1 is 4. How would you proceed now? Well, one way you could do it would be to add all these up, and that's sometimes done. Just add these up, so you get 2, 3, 7, 8, 9, 10, 11, 12. So there's a total of 12 here away from the mean. You might say, well, it's not fair that the more numbers there are, the more spread out seems to be. So you could divide by how many numbers there are, divide by the 5, so 12 divided by 5, and that will give you the average spread away from the mean. And that's called that's sometimes used, and that's called the mean absolute deviation from the mean. But it's not really that often used because it doesn't turn out to be so useful as the other one we use. The one we use is designed to cope with another problem, which is really these here should be negative, because 2 would mean I'm 2 above the mean at 7. Here I'm 2 below the mean, so I've got to put a negative 2. And here I'm 4 below the mean. And now if we added these up, then some of these would cancel out. This one would cancel out with this one. This one would cancel out with those two. You'd actually end up with 0 spread around the mean. If you tried to add all those up and divide by anything, you'd end up with 0. But of course there is some spread. So to cope with that, to cope with this negative numbers, instead of just ignoring the negatives, which is what you do if you're calculating the mean absolute deviation, it's not often used, what we do is cope with these negatives by squaring all the numbers. So, in terms of steps, the first one is find the mean. Second one is find deviations from the mean. Third one is we square the deviations. That's awful handwriting. Never mind. Now, the point of squaring is that minus 4 times minus 4 gives you plus 16, because negative times negative is a positive. So this gives you plus 4. Negative 2 times negative 2 is plus 4. then 1 squared is 1, 2 squared is 4, 3 squared is 9. And you add all those up. So the next step is, the fourth step, is you find the mean of these. So here we need to add them all up. So it's 20, 25, 28, 37. Just check that again because I'm going wrong a lot today. 20, 21, 20, it was wrong. 20, 25, 20, 21, 25, 34. Let's find that my mental maths is not good when I'm lecturing. 21, 25, 34. So finding the mean means you then divide that by 1, 2, 3, 4, 5, because there's 5 numbers. So you're going to get 6 and 4/5, or 6.8. Now we're trying to work out the standard deviation, but at this stage, when we've worked out these squared deviations and worked out the average of those, you get 6.8. That's actually got a name in itself. That's given us something called the variance. So the variance of our original numbers is 6.8. Just as the mean is often written with this symbol here, the variance is sometimes written using this symbol. Because that will become clear in a minute when we do the last step, which is 5, a bit more room here, square roots. Press the square root button on your calculator. And you should be rewarded with the standard deviation. I'm just going to do that in pink because it's such a great shade on this computer. So square root the 6.8, for which we need to dial up calculator. Square root on this is a bit awkward. 2.607. That's got 2.608. That gives you standard deviation. And standard deviation is written this symbol, which is the Greek letter for S for standard deviation. So because the variance is just the square of that, that's why that's written as squared. So it's variance and standard deviation, very, very closely related. Once you have variance, bash your square root button, you get 2.608. If you square that, you get 6.8. So that is another measurement of the standard deviation. Now if we hop over to our friendly Excel, we'll see I've got these numbers I originally put in there. You can see how you do it in real life, because you'd never bother using a pen in real life. You just put in the formulas. It already works. We already know how to do this. This is the average. Quite nervous that we're going to get different answers, and I have to go through that again. Dev P, I'll explain what the P is later on. Standard deviation P is the formula. Those numbers is going to be 2.60. Yes, exactly. Oh no, I've done the standard deviation. That's the standard deviation. If you really wanted the variance, it's var P. Yeah. So that corresponds to the numbers we got. And as you can see, 1,000 times easier just to use these formulae built in. Much easier to type var for the variance and stdev for the standard deviation. But the principle you should bear in mind, even though you might never do it again, is it's important to bear in mind that what that's really giving you is a measure of how spread out these numbers are from their own mean. And it's done that by looking at the deviations, squaring them, and work out the average squared deviation. So the variance is the mean squared deviation from the mean, and the standard deviation is the square root of the mean squared deviation from the mean. But having seen that, in your whole future career in using stats, you can just concentrate on plugging numbers into a formula now. So if we can return to the presentation, this then lets us add on the two measures of spread which are most frequently used, very closely related, variance and its square root, standard deviation. And a lot of the statistical techniques that you'll see used, and you may go on to use yourself, are based upon the variance and the standard deviation. It's crucially important to know how numbers are spread out. We've seen how we can look at the level and the spread of individual variables, such as age or income. We can use similar descriptive statistics to look at relationships between variables, which is where things get much more interesting when we're trying to study development issues. For example, here I'd like to look at a relationship between a nominal variable, which is one of these categorical things over here, and one of the numerical variables, which is these scale variables here. So I'm going to look at differences in income between the different languages, that's the ethnic groups. So we go back to the spreadsheet of values. We're going to try and look at the difference between these language groups in this variable here, income, which is a scale variable. So to recap what you do, you put the formula in, and the values here are in income are between H3 and we'll just do it like this, H3 and goes down to H32. So that's the formula we end up with, equals average H3 to H32. Enter that and move it over there. More sensible place for it. So the mean of income for everybody is 279 units. Now, I really would like to compare, instead of looking at everybody's income, break it down into linguistic subgroups. Now, an easy way to do this in Excel is to make Excel just show you these one at a time. So we'll look at the RJETs, then the Lengits, then the Earden. On the Data tab here, if you press Filter, make sure you click up here first, press Filter, then you see these little arrows appear here. What you can do then is press the arrow next to Language, and then it shows you all the different languages there are. Press that and they're all clear, and then just select the one you want, RJETs. Now before I do this, notice the mean for everybody is 279. Press OK. And now you've just got the RJETs there. You could, if you wanted, go for just the Lengits. I'll give you just the Lengits. This is extremely useful in Excel when you have long, complex spreadsheets, just to winnow out what you'd like to look at. Problem is though, when I just select the RJETs, I find that the mean income is still showing the same as the mean for everybody. And it was the same when I was just showing Lengits. Unfortunately, this formula, average, it gives you the average for all of these cells here, even the ones that are temporarily hidden, because I'm only looking at the RJETs. So it doesn't really work. However, all is not lost, because Excel realised that lots of people want to do this kind of thing, so they built a special function in that you have to use instead of average. And it's this. It's called subtotal. And when you press subtotal, you get this list of things here, and you can, if I put 1 here, then it's going to be the average, but I can put in any of these other things. So for a start, I'll put 1, because that's average. And then you put a comma, then you put in the same list of cells as usual, so it's C3, H3 to H32, that's as before. So it looks as though it's doing the same thing, but this subtotal will only give you the average for the visible cells. In other words, the RJETs. So 231. So the average income for the RJETs is 231. While we're doing this, let's look at the spread among the RJETs as well. So we'll look at the standard deviation for each group. What one here is this one, stdevp was the formula we used for standard deviation. The equivalent of that is to put just an 8 here in the subtotal function. So you still use subtotal, but you just put 8 instead. Cells are the same with the numbers in, H3 to H32, so 24. So this gives you a measure of how widely spread the income is, how much inequality there is between people in the RJET community. Once you put those two formulas in, you can just copy that into your table over here on the presentation, and then go back to here, get rid of RJETs and go to the next one in alphabetical order, which is Lengits. You can see that's their average, and then finally look at that's theirs. If you're using specialist software like SPSS, it'll do it even more easily than this in a couple of clicks. But in Excel, this is about as good as you can do. So what I do now is I go back to this presentation and I just fill in these numbers. And we can see using this that mean income among the Lengits is the highest, followed by the Eden and the RJETs. And again, there's much more dispersed, much more inequality between one person and the next in the Lengits. Pretty much following the order of size. Eden's less, RJETs much less. So actually getting over 4 times as much inequality or difference between the different groups in the Lengit compared to the RJET. So RJET's overall poorer but slightly more equal. Now, that's the relationship between nominal and scale variables. Now, if I look again at a difference between nominal ones, like between male and female, or between linguistic group, but this time I want to look at some of these numbers here. Now, these views, which are rankings, strictly speaking, they're what we call ordinal variables. So the differences between 1 and 2 and 3, we can't really be sure how much exactly. Is from 1 up to 2 the same as from 2 to 3? Can't be sure. All we know is that 2 is more than 1, and 3 is more than 2, and 4 is more than 3. But how much people's views increase each time, it's impossible to measure. And whether or not the difference for one person going from 3 to 4 is the same as another person, we can't tell. So we could compare the means again, but how can we interpret it? And I've given a very simple example here, even simpler than that, where I have 2 small groups of 3 people ask for their views on development aid. Between 0, is it unimportant to give development aid, or is it vital? Anyway, I haven't put any options for saying it's actually bad, but I've gone from 0 up to 5. So imagine that these are the answers here. If we look at the mean numerical response, if you work it out, it's actually 3 for each group, because each row adds up to 9. So 9 divided by 3 is 3 for each group. But can we assume that the strength of feeling is the same in each group from this? The numerical response is the same, the mean numerical response. Can we assume this shows that the strength of feeling is in any sense on average the same in each group? Well, what you're doing if you say it is you're assuming that the fact there's the first person here, instead of saying 1 has said 2, there's 1 up here. That compensates exactly for the strength of feeling going from 4 down to 3. So can we make that assumption that for a person giving this score instead of this score is the same as some other person giving this score instead of this score? These are all different people. I think that's a difficult thing to assume. In which case, this mean is a poor guide to comparing actual views. Another way of thinking it is that for the mean, what you're doing is you're adding up the total. So if this was income, you can add up the total amount of money and share it out. That makes sense. But can you add up the total views of people and then share that strength of view out? And again, add up the total views of this group and share it out between 3 people. That's kind of a bit odd. If instead we use the median, which means the middle person here is the second person, their view is 4. The middle person here is the second person, their view is 3. In that case, the median is 4 for the first group and 3 for the second group. Is that a better comparison of views? In a sense, what we're doing here with the median is we're looking at the views of the average person, instead of trying to work out what the average or the mean view is, the views of the average person. In which case, the group 1 would seem to have more positive group views, because there's 2 people that are going high ranks here, as compared to here, where there's only 1 with a high, 1 with a low, and 1 in the middle. So arguably, the median's a better guide here. If we try and apply this back to our descriptive statistics, I'll show you how you do this. It's difficult to get these medians out because there's no, once you've got them grouped, there's no function that will give you the median in the subtotal. So what you'd have to do is this. To get the median for the Earden is views on privatisation. What you actually have to do is copy these. Well, unless you can actually do it by eye. And use the built-in median function once you've copied them down here. It's a sort of workaround. That'll give you 3. So that's why I get the 3 here for the Eardens. So a little bit awkward in Excel. But in the case of this views on privatisation, in actual fact, it doesn't make a great deal of difference whether you use mean or median. Leggett turns out the highest, Ardiet the lowest, and the Earden somewhere in between. Now, if you read books on methodology and sometimes methodological sections of papers, authors will point out that for ordinal data, the mean is questionable and really you should use the median for ordinal data. And strictly speaking, that's true, in my view. When you're trying to get at, instead of the score, you're trying to get at the feeling behind the score, you should be looking at median, so the views of the average person rather than the average view, which doesn't mean anything. But in practice, often people just forget this or just ignore it, and they just give you the mean anyway. For example, in our evaluations of courses at university, we just look at the mean scores that people give. And as you see, often it doesn't make a big deal of difference anyway. But philosophically, this is more correct. And you'll see that mentioned in various places. So that's how we can compare the relationship between nominal and ordinal variables using either the mean or the median. We often need to look for a relationship between two scale variables, such as age and income here. We could use the approach of mean incomes. We could look at the mean income for all 65-year-olds, mean income for 68-year-olds, 38-year-olds, 54-year-olds, and so on. But there'd be many, many different groups. Or we could put these into ranges, so look at the mean income for people in their 20s, 30s, 40s, and that would be okay. Another very common way of looking at relationships between scale variables is to use correlation, which is what we'll do here. Visually using a scatter chart and using a statistic, which is a correlation coefficient. Let's just show you how you do these two in Excel. We have age and income here. What I'd like to do is insert a scatter chart. My tip is, before you put in charts in Excel, I recommend that you click well away from the data so that there's at least one blank column. Otherwise, I find it tries to make the chart itself and usually makes more of a mess than helping you. So do that and then click on Insert. Well, let's just show you what you get. If you click in here and do Insert, Scatter, it gives you a revolting mess. So I wouldn't do that. Click outside the chart and then do Insert, Scatter Graph, just a basic one, basic option. Then you start with a blank sheet. Now you right click inside here, say select data. I need to add a new data series. And here you can give it a name if you want to. Age versus income. The important ones are the X and Y values. So X is the values that should appear along here. So you can type in the range of cells as before here, or you can press this kind of symbol here, which I always think of as a postbox, but it's not really. And then that lets you shade in with the cursor, with the mouse there from here down to, the age goes down to here. And you press that again. And then here from down to there for income. Okay, check it's okay. And there we've got your chart. You can see maybe if you're used to looking at, if you've ever seen a correlation before, what you're looking for is some sort of pattern, some sort of suggestion of a line. For example, as age goes up along here, does income go up? One tip is to get rid of this because you don't need that, because there's only, we know that it's age versus income. The other thing is there's a lot of wasted space here. We could do with starting a bit higher up, say 150 or so, or even higher, and going up only to 500, and here cutting up that wasted space here and going from 20 up to 90. So you can do that by clicking on the thing, the axis, doing Format Axis, and overriding it from automatic. Say I want to fix the minimum at 150 and fix the maximum at 500. So that's got rid of the spare space at the bottom and the top. Same thing on this chart, for this axis. Format horizontal axis, make it start from 20, go up to 90. So I'm using more of the chart body. It could be there's a slight suggestion as age goes up, income's increasing, but it's hard to tell visually. So the other thing we can use as well to complement a scatter graph is to calculate a coefficient. And for scale variables, the most commonly used one is actually Spearman's correlation coefficient. I'm not going to go into the formula for Spearman's correlation coefficient. You'll find it in all the textbooks and readings and so on. But it's very easy to calculate in Excel. So correlation. Just put the first few letters of a coron, that's it there. And then you just use the cursor as before to highlight that there, and then put a comma, and then highlight the other one. Doesn't matter which order you do it. So as a formula, you type it in like that, by hand if you wish. And here it gives you this value of positive 0.03682, which is a pretty weak positive correlation. So we find Spearman's correlation coefficient is positive 0.037 to two significant figures, and really that's a negligibly weak positive correlation. It's almost nothing really between those two. So very little evidence here of any correlation or any relationship between age and income. So look at a couple of other examples of correlation. Well, first of all, we'll note here that the value you get is always between -1 and +1. -1 means a perfect negative correlation. +1 means a perfect positive correlation. 0 is no correlation at all. Really what we got was practically 0. Here's another couple of correlations. So here's one where I looked at primary enrolments against infant mortality. I also put some labels on the axis, which you should always do. So as primary enrolment increases here, it looks like age dependency ratio. Oh, an error in the labeling. That should say age dependency. Perhaps I have time to fix that. Primary enrolments against age dependency. Here we get a Spearman's correlation coefficient of 0.79, so a strong positive correlation. That's a pretty clear relationship. And that data, as always, comes from the World Development Indicators, the World Bank, as all the data I'm using in this part of the presentation comes from. Another example, this one looks slightly different because I created this in the SPSS statistical package. But it works in a similar way. Here we've got primary enrolments, and here's the population over 15 which is illiterate. And this suggests that as primary enrolment goes up, illiteracy comes down. So countries with nearly everybody enrolled in primary school have relatively low levels of illiteracy, where primary enrolment is very high, or very low rather, illiteracy is very high, as you'd expect. This again is a very strong correlation, but it's a strong negative correlation. So 0.71 is close to 1, so it's strong suggestion of a line, but it's negative because as one variable increases, the other one decreases. And the final example here is the relationship between illiteracy and the number of people per doctor. So countries with a great deal of illiteracy, there are many, many people per doctor. But countries where most people are literate, there are relatively few people per doctor. And you might like to think about whether that is what you might expect, and what's the causality here? Does the illiteracy of the population increasing cause there to be fewer doctors, in other words, more people per doctor? Or is it the number of people, is it when you have more doctors available, down here, does that decrease illiteracy, or is there some other causal connection going on? Looking at the numbers, this is 0.54, which is a reasonably strong or fairly strong positive correlation. You need to get used to looking at a pattern like that and thinking, actually, that shows pretty clear evidence there's a link between these variables of some sort, even though we can't say anything about causality because it's only correlation. And I'll note here in passing that if you do want to look at, I can get back to the spreadsheet. If you do want to look at links between these ordinal variables here, You can draw a scatter graph in the same way, and that will give you an indication of any links. But if you do a correlation, you should use something called Spearman's correlation coefficient, which doesn't have a formula in Excel, or you can make your own formula if you want to look the formula up. SPSS would do it automatically for you. But strictly speaking, you should use Spearman's rank correlation coefficient instead of Pearson's one here. But you can do a scatter graph in the same way. To describe relationships between two nominal variables, we can't use things like means and medians because there are no numbers for these. The numbers at least are not meaningful. So we can't put them into order, we can't work out averages or correlation coefficients. What we can do with these is to use cross-tabulation, where you have a table like this, and this is called a cross-tabulation, where the categories in one nominal variable are down here, it's language, and the other, which is sex, are along here. And you simply count how many female arjets there are, female lenggits, and so on. And you look for patterns in a way that I'll show you in a moment. First of all, how to get these in here. Statistics software will do it automatically. You can get some help in Excel using the filter commands and other ways. If we filter the data again, so filter to get the females, you can simply count. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 females in there. And if you want the female arjets, you can do it by eye, or you can just, keeping the filter on females, you can see you've got 1, 2, 3, 4, 5, 6. And then you've got Eardens, 3 Eardens, and there are no lenggits. And then you can change it to males. You've got the Eardens there, count those. Count the arjets and so on. Yeah? So you can count each combination just by using the filters. If you have a bigger data set, you can put some formulae in, similar to ones that I showed you before for counting men and women, or probably best if you've got statistical software, use that, otherwise you've got a fiddly job. Anyway, once you've counted them up, go back to the table and enter in the values like this. So you get a pattern like this. Now, I think maybe you can kind of see there's a pattern here, but a good way of revealing it is to look at what's called the row percentages and the column percentages, like this. So there's my original table. What I've done here is I've looked at row percentages. We're working out, replacing these values by what percentage of the total is here and what percentage is here. So in this row, what percentage is in the first column and the second column. And here I've got percentages going down to 100% here. The way we can interpret this is to say, well, first look at the total. So in the row, if you look at the total people here, 30% of all the people are females and 70% are males. If I look at the Earden ethnic group, among the Earden specifically, 21% are female and 78.6% are males. So it's slightly more than among the general population, or among the general sample, slightly fewer Eardens. Lenggits, even more striking, no females at all, they're all males. And Arjets, completely reversed, more females than males. So overall among the population, 30% female, 70% male. Among the Arjets, it's 60% female and 40% male. Now we can look at the breakdown another way by saying, well, look, putting percentages in columns, look at the totals. Well, of the total people, 33% are Arjets, 20% Lenggit, 46.7% in. But then when we look at the two sexes, we can see that whereas overall there's 33% Arjet, there's far fewer males, only 20%, 19%, and very many females Arjets. So among the females, the proportionally much higher percentage of Arjets. No Lenggits at all, whether that's nearly a third of males, and relatively few Earden compared to males. Yes. So 52%, slightly higher among the males and slightly lower among the females. So you can see a number of small patterns there, but the main pattern is there's an association between females and this ethnic group. So if this data is head of households, among head of households, they're more likely to be head of households when they're in the Arjit group than among the other group. And it looks like there are no female head of households in the Lenggit group. So that's the main result we get from this.